For generations, we thought the solar system was complete 8 planets, mapped, named, and understood. But beyond Neptune, distant objects are moving in patterns so unnatural that scientists suspect something massive, invisible, and still unconfirmed is shaping their orbits. Keep watching and subscribe, because those signals may point to something far worse than Planet 9. Get ready. Now, let's begin. Beyond Neptune, space gets messy. That's not a casual observation. It's a scientific fact that astronomers spent decades confirming, cataloging, and ultimately accepting as the natural state of things. The Kuiper Belt stretches from roughly 30 astronomical units out to about 50 astronomical units from the Sun, a vast, frozen graveyard of leftover material from the solar system's formation 4.5 billion years ago. Hundreds of thousands of icy objects tumble through that region, chunks of rock and frozen gas, some the size of mountains, some the size of cities, none of them particularly interested in keeping order. Their orbits point in different directions. Their trajectories cross and diverge. From above, the Kuiper Belt looks less like a structured ring and more like a swarm of bees after someone kicked the hive. Chaotic, unpredictable, random. And that randomness made perfect sense. Physics demanded it. When the early solar system was still a churning disk of gas and dust, the gravitational nudges of the giant planets, Jupiter, Saturn, Uranus, Neptune flung enormous amounts of material outward into the outer solar system. Those objects scattered in every direction, settling into orbits that reflected the chaos of their origins. No two were exactly alike. No pattern was expected. No pattern was found. For most of the 20th century, that picture held. The Kuiper Belt was simply the solar system's attic, cluttered, disorganized, and mostly ignored. Then came 2 astronomers with better telescopes and worse luck. Between 2003 and 2016, Chadwick Trujillo and Scott Shepard were doing what outer solar system astronomers do, cataloging the most distant, most difficult to see objects at the farthest reaches of the Sun's gravitational reach. These weren't ordinary Kuiper Belt objects. They were tracking what scientists call extreme trans-Neptunian objects, ETNOs, the loneliest pieces of real estate in the solar system, orbiting so far out that a single trip around the Sun takes thousands of years. Trujillo and Shepard weren't looking for a pattern. They were just looking. What they found stopped them cold. 6 of the most distant ETNOs objects, whose orbits reached to the absolute outer edges of the solar system, all had their perihelia, the closest point of each orbit to the Sun, clustered within the same narrow region of space. Not spread randomly across 360 degrees, the way chaos theory and 4 decades of observation said they should be. Clustered, aligned, all pointing within fewer than 30 degrees of each other. The probability of that happening by chance with no external force involved, just random cosmic luck, is less than 0.007%. Let that number breathe for a moment. Less than 0.007%. Imagine placing 6 compasses on a table. You spin each one randomly, let it settle, and look at where the needles point. The odds that all 6 land within 30 degrees of each other, not exactly the same direction, just roughly the same neighborhood, are already vanishingly small. Now imagine those 6 compasses are not on a table but scattered across billions of miles of space, each one following its own gravitational history, shaped by 4 billion years of planetary interactions. Each one should be pointing somewhere completely different. And yet, all 6 are pointing the same way, not because they agreed, not because of some coincidence in how they formed. The only explanation that survives basic physics is that something is pulling them, something with enough gravitational mass to reach across billions of miles of empty space and quietly, persistently, bend the paths of 6 different objects toward the same invisible corner of the sky. The logic is almost uncomfortably simple. You don't get alignment without a source. A compass needle doesn't point north because it likes north. It points north because there is a north to point to. If nothing is out there, then what is doing the pulling? Trujillo and Shepard published their findings. The astronomical community leaned in, and right there, quietly buried in the data of 6 icy objects most people had never heard of, was the first concrete suggestion that the solar system might contain something no one had ever seen. The reaction from the broader scientific community was a mixture of genuine excitement and careful skepticism, which is exactly how science is supposed to work. Some researchers immediately began running orbital simulations. Others started scanning their own datasets for similar alignments. A few pointed out, correctly, that 6 objects is a small sample size. The universe has surprised astronomers before with patterns that turned out to be statistical noise. But here's the thing about statistical noise. It tends to dissolve when you add more data. The clustering of ETNOs did not dissolve. As more distant objects were discovered and cataloged in the years that followed, the alignment stubbornly persisted. Not perfectly, not in a way that closed all debate, but enough to keep the question alive and growing louder. It's worth pausing to appreciate the particular irony embedded in this discovery. Astronomers spent decades building the scientific consensus that the Kuiper belt is structurally disordered. Papers were written, models were validated, textbooks were updated. The chaos of the outer solar system became one of those bedrock assumptions that researchers stopped questioning because the evidence seemed so thoroughly settled. Then the data walked in and said not quite. The clustering of 6 orbital perihelia is the kind of finding that, in isolation, might be dismissed as an interesting statistical anomaly, the sort of thing that generates a paper, a few conference presentations, and a follow-up study 2 years later. Science produces those regularly. Most of them fade. This one didn't fade. It got louder. Because it turned out the orbital clustering was only half the problem. But the clustered orbits are only half the story. The other half involves the entire solar system tilting. The solar system was born flat. 4.5 billion years ago, a vast cloud of gas and dust began collapsing under its own gravity. As it collapsed, it spun. And as it spun, conservation of angular momentum, the same basic physics that makes a figure skater pull her arms in to rotate faster, caused the cloud to flatten into a disk. The sun formed at the center. The planets coalesced from the material in that disk because they all came from the same rotating plane of material. They all ended up orbiting in roughly the same geometric flatsheet, the way grooves on a vinyl record all lie on the same surface, parallel and orderly, each one following the plane defined by the disk that made them. This is called the ecliptic plane. Every major planet in the solar system orbits within a few degrees of it. Mercury tilts a little, Venus tilts a little more, but the overall architecture is unmistakably flat, a coherent, unified disk that reflects the conditions of the solar system's birth. This is not a debated point. This is not a working hypothesis. Astronomers confirmed it through 2 centuries of observation, and the physical logic behind it is airtight. The sun sits at the center of all this, spinning on its own axis. And here is where the geometry should be clean, the sun's equatorial plane, and the plane in which the planet's orbit should be aligned. Same disk, same origin, same angular momentum they should match. They don't. The combined orbital plane of the 8 planets is tilted 6 degrees relative to the sun's equatorial plane. 6 degrees doesn't sound catastrophic. It isn't visible to the naked eye. You can't feel it, can't observe it from Earth without precise instrumentation. And for most of human history, no one had the tools to even notice it. But in the context of planetary physics, 6 degrees is not a rounding error. It is an anomaly confirmed, persistent, and stubbornly unexplained. The confirmation came through helioseismology, the science of studying the sun's internal oscillations, essentially, listening to the vibrations the sun produces as it pulsates. The way a doctor might listen to a heartbeat to infer what's happening inside the chest. By analyzing those oscillations with extraordinary precision, scientists were able to map the sun's rotational axis with high accuracy. The result was unambiguous. The solar equator and the planetary orbital plane are misaligned by 6 degrees. No measurement error, no instrumental artifact. 6 degrees. Real, repeatable, verified. And no one could explain it. The solar system formed from a single rotating disk. Everything should share the same angular momentum baseline. There is no internal mechanism, no process operating within the known 8-planet system that should have produced a 6-degree tilt between the sun's spin axis and the plane in which its planets orbit. Every model built on the assumption that the solar system is a closed, complete, self-contained system hits a wall at this number. Think of a vinyl record spinning on a turntable. The record is flat, the grooves are flat, and the needle reading those grooves is supposed to sit parallel to that surface. Now imagine the needle is tilted 6 degrees off the plane of the record, not because the needle is broken, not because the turntable is defective, but because someone has wedged something underneath one corner of the table, something you can't see from where you're standing. The table looks level, the record looks flat, but something underneath is pushing one side up, just slightly, just enough to throw the geometry off. That is the 6-degree tilt. Precise, measurable, and pointing at a cause that isn't inside the system you can see. In 2016, Konstantin Batygin and Mike Brown at the California Institute of Technology published a paper that placed both anomalies, the orbital clustering of the extreme trans-Neptunian objects from Part 1 and the 6-degree tilt of the planetary plane, into a single computational framework. They ran the numbers. They built the models. And what they found was that both anomalies could be explained simultaneously by a single distant body, massive, far out, and moving on an orbit tilted and elongated far beyond anything in the known solar system. Not two separate forces, not two unrelated coincidences. One object, one gravitational source. 2 fingerprints? The mathematics was not merely suggestive, it was structurally elegant. A planet with a mass between 5 and 10 times that of Earth, orbiting the Sun on a highly elliptical path at an average distance somewhere between 300 and 700 astronomical units, inclined at roughly 30 degrees to the ecliptic plane, placed in the correct orbital orientation, produced in simulation both the clustering of distant orbital perihelia and the 6-degree tilt of the planetary plane. The fit was not perfect. No model ever is, but it was far too good to dismiss. 2 independent anomalies, 2 separate data sets, one proposed explanation threading through both. This is the part that deserves a moment of genuine weight. The 6-degree tilt has almost certainly existed for billions of years. The solar system has been carrying this misalignment since long before multicellular life appeared on Earth, since long before the continents took their current shapes, since long before the first human looked up at the night sky and wondered what was out there. The signal was always present. The solar system has been broadcasting it continuously, written into the geometry of every planet's orbit, encoded in the spin axis of the sun itself. Nobody heard it until the 21st century. That's not a failure of intelligence. It's a failure of instrumentation, combined with the deeply human tendency to assume that the system we can see is the complete system. For most of scientific history, the 8 planets were the solar system. The idea that something massive enough to warp the geometry of the entire planetary disk might be lurking far beyond Neptune, invisible and unmapped, simply didn't fit into the picture anyone was working with. The data changed the picture, not gradually, not gently. It changed it the way a crack appears in a wall you thought was solid suddenly visible, impossible to unsee, demanding an explanation for why you didn't notice it sooner. 6 degrees, 4.5 billion years, and a signal no one was listening for, sent continuously in plain sight, waiting for someone to finally ask the right question. When two separate anomalies point to the same source, science is obligated to give that source a name. Astronomy has a long and quietly astonishing tradition of finding things before seeing them. In 1845, a French mathematician named Urbain Le Verrier sat down with nothing but a stack of orbital data and a sharpened pencil. Uranus, discovered in 1781, was misbehaving. Its observed position kept drifting from where Newton's laws said it should be. Small deviations, easily dismissed at first. But Le Verrier didn't dismiss them. He reverse-engineered the perturbations, traced the gravitational disturbance backward through the mathematics, and calculated where an unknown planet would have to be in order to produce exactly those deviations. He published his prediction in 1845. Astronomers at the Berlin Observatory pointed a telescope at that region of the sky in September of 1846 and found Neptune within the first night of searching less than 1 degree from where Le Verrier's math said it would be. No photograph, no prior observation, pure mathematics, confirmed by light. It remains one of the most elegant moments in the history of science. The universe obeyed an equation before anyone could see the object the equation described. What Badigan and Brown did in 2016 sits in that same tradition. They looked at orbital anomalies, they ran the numbers, and the numbers pointed at something. What the mathematics predicted was not small. The proposed object, now broadly referred to as Planet 9, carries an estimated mass of approximately 6.6 to 10 times the mass of Earth. That places it firmly in the category of ice giant planets, the same class as Uranus and Neptune, worlds built from rock, metal, and a thick mantle of water, ammonia, and methane ices compressed under enormous pressure. In raw terms, it would be a substantial world, not a gas giant like Jupiter or Saturn, but far larger and more massive than anything in the inner solar system. The size is not the surprise. The orbit is. Every planet in the known solar system travels on an orbit that is, to varying degrees, roughly circular. Mercury has the most elliptical orbit of the 8, with an eccentricity of about 0.2, meaning its distance from the Sun varies, but not wildly. Earth's eccentricity is just 0.017, barely distinguishable from a perfect circle. These are orderly paths, worn smooth by billions of years of gravitational settling. Planet 9, according to the models, travels on an orbit that is radically different in character, highly elliptical, dramatically elongated, tilted roughly 30 degrees relative to the plane in which the other planets orbit. Its closest approach to the Sun perihelion is estimated somewhere between 300 and 400 astronomical units. Its farthest point, aphelion, stretches somewhere between 700 and 1200 astronomical units, depending on which refined model you consult. Think about what that orbital shape means in human terms. If Earth is a car driving slow, steady laps around a stadium track, same lane, same speed, reliably completing a circuit every 365 days, then Planet 9 is something else entirely. It's a vehicle running an enormous oval course that begins somewhere vaguely near the stadium, then stretches outward through downtown, past the suburbs, all the way to the far edge of the metropolitan area, and then loops back again. One full circuit of that course takes between 10,000 and 20,000 years of Earth time. 10,000 years ago, humans were building the first permanent settlements. 20,000 years ago, the last ice age was still in full grip. Planet 9, on a single orbit, spans the entire length of recorded and pre-recorded human civilization, from the first clay tablets to the James Webb Space Telescope, and doesn't even complete one full loop. That is not a planet behaving like its neighbors. That is a world living by a completely different set of rules in a completely different corner of the solar system, on a time scale that makes human history look like a single afternoon. You're probably thinking, if it's that massive, why hasn't anyone seen it? That is exactly the right question. A world 6 to 10 times the mass of Earth sounds enormous by any intuitive measure. Jupiter, the largest planet in the solar system, is 318 times the mass of Earth, and it blazes in the night sky even to the naked eye. Saturn, at 95 Earth masses, is visible without a telescope. Even Neptune, at 17 Earth masses and 30 astronomical units away, was confirmed by direct observation within hours of being targeted. So why would something 10 times Earth's mass remain undetected? The answer requires confronting the fact that intuition about size is almost completely useless in astronomy, because intuition ignores distance, and in this case, distance is the entire problem. Finding something 10 times the mass of Earth in the outer darkness of the solar system is roughly like looking for an elephant in an unlit room. The logic sounds simple. An elephant is enormous. It should be easy to find. But if the room is large enough, if it stretches, say, across 1 trillion football fields laid end to end, the elephant becomes effectively invisible. You're not looking for an elephant anymore. You're looking for a faint smudge in an incomprehensibly vast field of other faint smudges, most of which are background stars in distant galaxies, all of them demanding your attention simultaneously. The darkness is not a poetic metaphor. It is a physical condition that directly determines what telescopes can and cannot do. And at the distances Planet 9 is predicted to occupy, the darkness wins by a margin that is almost insulting. Size is not the problem. Distance is the real enemy. Astronomical distances are measured in astronomical units, and the baseline is fixed. 1 astronomical unit is the average distance from Earth to the Sun, roughly 150 million kilometers, or about 93 million miles. It's a useful unit precisely because the solar system, at human scales, is so large that miles and kilometers become meaningless very quickly. Neptune, the outermost confirmed planet, orbits at an average of about 30 astronomical units from the Sun, 30 times the Earth-Sun distance. Light takes roughly 4 hours and 10 minutes to travel from the Sun to Neptune. Voyager 2, launched in 1977, reached Neptune in 1989 after 12 years of continuous travel at speeds no human vehicle had ever previously sustained. By any ordinary standard of measurement, 30 astronomical units is extraordinarily remote. Astronomers spent most of the 20th century treating Neptune's neighborhood as the practical boundary of the solar system. The Kuiper belt extends a bit beyond it, and the scattered disk reaches further still. But for practical purposes, for the purposes of anything we could actually study with confidence, Neptune represented the outer wall. Planet 9 doesn't live anywhere near that wall. The predicted perihelion of Planet 9, its closest approach to the Sun, the point on its orbit where it would be most detectable, sits somewhere between 400 and 800 astronomical units from the Sun. Current best estimates from the most refined models, incorporating the latest ETNO orbital data, center around 500 to 600 astronomical units for the most likely perihelion distance. At aphelion, the far end of that stretched elliptical orbit, the distance climbs to somewhere around 1,200 astronomical units. Neptune is at 30. Planet 9, at its nearest, is somewhere between 400 and 800. At its farthest, it reaches 1,200. That is more than 40 times farther than Neptune. In some configurations, more than 40 times farther than a world that already took 12 years for our fastest spacecraft to reach. To make that distance feel real, consider this geography. Place the sun as a single light bulb standing at the center of Times Square in New York City. On that scale, Earth orbits about 1 block away. Neptune sits at the end of a long city block, maybe 300 or 400 feet from the light, still in the lit zone, still within the warm radius of the bulb's glow. Planet 9. It's somewhere in New Jersey, past the Lincoln Tunnel, past Newark, somewhere out in the dark stretches of the suburbs where the city light has faded to almost nothing and the streets have no lamps. The sun, that same bulb in Times Square, provides essentially no useful illumination at that distance. And Planet 9, sitting in that darkness, has no light of its own. This is the core of the detection problem. And it's not a technology problem. It's a physics problem. At 700 astronomical units from the sun, sunlight has spread out so dramatically diluted across the surface of an imaginary sphere with a radius of 700 astronomical units that it carries only a tiny fraction of the energy it carries at Earth's distance. The inverse square law of light intensity is unforgiving and precise. Double the distance, and brightness drops to 1/4. Increase the distance by a factor of 40, and brightness drops by a factor of 1,600. 1,600 times dimmer than what reaches Neptune. And Neptune is already so faint that for most of human history, it was completely invisible to every observer on Earth. At that light level, even a world the size of Planet 9 cannot reflect enough sunlight back toward Earth for any current optical telescope to detect it against the background noise of the sky. The reflected signal is simply too weak. It drowns. Not because our telescopes are bad. The best optical telescopes currently operating are extraordinary instruments, but because the physics of light propagation over that distance produces a signal smaller than what those instruments can reliably distinguish from noise. The planet isn't hiding. It's just standing in the dark, beyond the reach of any light that could bounce off its surface and carry the news back to us. This is where the hunt changes strategy entirely. If reflected sunlight is too faint to detect, then astronomers cannot look for Planet 9 the way they found every other planet in history. By catching the light, it bounces back. They need something else, something that doesn't depend on the sun's light reaching the planet and returning to us. They need to look for what the planet itself is generating. If you can't see the reflected light, listen for the warmth instead. Every object warmer than absolute zero radiates energy. Not metaphorically, not approximately. Physically, measurably, inescapably, anything with a temperature above 0 Kelvin emits thermal radiation outward into its surroundings. This is one of the bedrock principles of physics, confirmed so thoroughly and applied so broadly that it barely registers as a discovery anymore. It's simply how matter behaves. The human body runs at about 37 degrees Celsius and radiates infrared energy continuously, which is why thermal imaging cameras can find people in complete darkness, why heat-seeking military systems can track warm engines against cold sky, why a firefighter's thermal camera can locate a person through a smoke-filled room that is completely opaque to visible light. The principle is the same in every case. Heat produces radiation. Radiation travels outward, and a sensitive enough detector can find the source even when every other form of detection fails. Astronomers understood this principle long before anyone proposed the existence of Planet 9. What took time was recognizing that it might be the only viable detection method for something sitting at the far edge of the solar system in conditions of near total darkness. The crucial precedent comes from the planets we already know. Neptune, 17 times the mass of Earth, orbiting at 30 astronomical units, emits roughly 2.6 times more energy than it receives from the Sun. That surplus heat is not coming from nuclear fusion. Neptune has no fusion core. It is residual thermal energy from the planet's formation 4.5 billion years ago, when the gravitational collapse of enormous amounts of material generated tremendous heat that has been slowly radiating outward ever since. Neptune is still cooling down from its own birth. The process is so gradual, and the planet so massive, that it will continue radiating that primordial warmth for billions of years to come. Uranus is a somewhat puzzling exception. It shows far less internal heat emission than Neptune, for reasons that remain debated, but the broader pattern is clear. Ice giant planets carry internal heat from their formation and radiate it into space in the infrared spectrum, independent of whatever sunlight they receive. If Planet 9 is an ice giant, if it shares the structural character of Uranus and Neptune, as the orbital models suggest, then it is almost certainly doing the same thing. Right now, somewhere out there between 400 and 1,200 astronomical units from the Sun, a world roughly 6 to 10 times the mass of Earth is breathing warmth into the void, sending infrared radiation outward in all directions, including toward us. Something 10 times the mass of Earth is exhaling heat into the universe, and we are trying to hear it from a distance of roughly 100 billion kilometers. That is the precise and not at all comforting situation astronomers find themselves in. The logical response was to look through archives. Not every telescope scans the sky in visible light. Japan's Akari Space Telescope, operated by the Japan Aerospace Exploration Agency, was designed specifically to map the sky in infrared wavelengths. It launched in 2006, operated until 2011, and during that time, conducted 2 full-sky infrared surveys, cataloging hundreds of thousands of infrared point sources across the entire observable sky with a level of coverage that no ground-based telescope could replicate. Akari wasn't built to find Planet 9. It wasn't built to find anything in particular. Really, it was a mapping mission, creating a comprehensive infrared atlas of the sky for the broader astronomical community to use. But its all-sky coverage made it uniquely relevant to the Planet 9 search, because Planet 9, if it exists, would have to show up somewhere in an infrared map of the entire sky. In 2021, a research team led by Teruyuki Hirano at the Tokyo Institute of Technology went back through Akari's archived data, specifically looking for unidentified infrared point sources objects that emit in the infrared but don't correspond to anything in the existing catalogs of known stars, galaxies, and solar system bodies. The methodology was painstaking, cross-referencing hundreds of thousands of detections against multiple astronomical catalogs, filtering out known sources, flagging anomalies. 2 candidates emerged, 2-point sources in the Akari infrared data that didn't match any known celestial object as of 2021. Both were isolated. Both appeared in regions of sky that had not been saturated by contaminating infrared sources. Neither corresponded to any entry in the major astronomical reference catalogs available at the time. The team published their findings with careful, deliberate language. These were candidates worthy of follow-up investigation, not confirmed detections. The distinction matters enormously in science, and Hirano's team was scrupulous about drawing it. The reason for that caution lives in the data itself. Akari was a remarkable instrument for its time and purpose, but its angular resolution, its ability to distinguish fine spatial detail, was limited by the physical constraints of the telescope's aperture and its position in low Earth orbit. At the distances where Planet 9 is predicted to exist, even a world significantly larger than Earth would appear as an unresolved point source, indistinguishable in shape from a background galaxy or an instrumental artifact. Akari could detect that something was there. It could not determine what that something was. Resolution is not a minor technical inconvenience. It is the difference between a clue and a confirmation. A smudge on a photograph might be a face or a smear of dust on the lens, and without enough resolution to make out features, you genuinely cannot tell. The 2 Akari candidates sat in exactly that ambiguous position, real enough to flag. unresolved enough to remain open questions. The science community had spent years looking for Planet 9, using cutting-edge optical surveys on some of the largest ground-based telescopes on Earth. Now, the best lead in the infrared came from a retired Japanese space telescope whose archived data had to be re-examined a decade after the mission ended. Hunting for a planet that may be 10 times the mass of Earth? Using data from a telescope that ceased operations in 2011 at a resolution insufficient to confirm what you found. That is the scientific equivalent of trying to identify a missing person using security camera footage from 2011 at 360 pixels possible in theory. Frustrating in practice, inconclusive by design. The infrared clues are still faint, but a newly discovered object just forced astronomers to redraw the entire search map from scratch. Separating real signals from background noise is not a problem unique to the Planet 9 search. It is the central technical challenge of all observational astronomy, present in every instrument, at every wavelength, across every era of the science. The James Webb Space Telescope, the most powerful space observatory ever launched, a 21-foot mirror cooled to within a few degrees of absolute zero, operating 1 million miles from Earth at the second Lagrange point, faces it constantly. Webb's own mirror and instrument housing, despite being chilled to extraordinarily low temperatures, still produce trace thermal emissions that must be calibrated out of every observation. Its detectors register faint signals from distant galaxies that must be disentangled from the diffuse infrared glow of interplanetary dust inside our own solar system. Even at the frontier of human engineering, noise is never absent. The art is in recognizing which part of the signal is real. The Akari candidates inherit this problem in an acute form. The two unidentified point sources from Hirano's 2021 analysis were not located near each other. They appeared in separate regions of the sky, which is, itself, a double-edged characteristic. Separation reduces the likelihood that both are the same type of instrumental artifact, since the same systematic error rarely reproduces identically in distant parts of the focal plane. But it also means they cannot both be Planet 9, which is a single object. At most, one could be the planet, possibly neither. Hirano's team ran the numbers on what the distance would need to be if one of the candidates was in fact Planet 9, working backward from the predicted thermal emission of an ice giant planet at various distances. Their estimate placed a matching object at approximately 500 astronomical units from the Sun. 500. That sits squarely within the range predicted by the refined Batygin-Brown models for the perihelion distance of Planet 9, and within the broader range considered plausible by independent analyses. The fit, on paper, is not uncomfortable. It doesn't prove anything, but it doesn't contradict anything either. And in a search this difficult, a candidate that survives basic cross-checking against the theoretical predictions is a candidate that deserves continued attention. The problem is what continued attention requires. To confirm or rule out an infrared point source as a solar system object rather than a background galaxy or an artifact, you need to detect its motion. Solar system objects move relative to background stars slowly for distant objects, but measurably so over months or years of observation. A background galaxy does not move on those timescales. If Akari's candidates are real solar system objects, they will have shifted position since 2011. Finding that shift requires a telescope with sufficient resolution and sensitivity to detect a faint infrared source in the same region of sky and compare its position precisely enough to register movement across more than a decade. Imagine trying to hear a single person whispering across the full width of the Grand Canyon while standing at the center of a stadium where a rock concert is playing at full volume. The whisper is real. The physics of sound guarantees it travels across that distance in some form. But the ambient noise, the crowd, the instruments. The reverb off every surface is so overwhelming that detection requires something far beyond ordinary human hearing. You would need instrumentation tuned specifically to that one frequency, shielded from the surrounding noise, positioned where the signal-to-noise ratio is most favorable. The infrared sky presents the same problem at a cosmic scale. Planet Nine's thermal emission must be distinguished from the infrared glow of billions of background galaxies. The thermal emission of dust within the Milky Way, the zodiacal light from interplanetary dust within our own solar system, and the residual warmth of the telescope hardware itself. All of that sits between us and the signal we're trying to read. This is where the instinct to reach for the James Webb Space Telescope runs directly into a structural limitation that no amount of mirror size can fix. Webb is built for depth, not breadth. Point it at a small patch of sky, and it will reveal objects so faint and distant that no previous telescope could have detected them galaxies from the first few 100 million years after the Big Bang. Atmospheric compositions of planets orbiting other stars, the thermal signatures of dust disks around forming solar systems. In targeted observation of a known location, Webb is extraordinary beyond comparison. But Planet Nine's location is not known. The search area, even after years of refinement, using ETNO orbital data, still spans thousands of square degrees of sky. Scanning that entire area with Webb, pointing it patch by patch across a search region measured in fractions of the entire celestial sphere, would consume an amount of telescope time that the scientific community cannot justify when Webb's schedule is competing with observations of the early universe, exoplanet atmospheres, and 100 other priorities. Webb sees deep. The Planet 9 problem needs wide. Those are different tools. The scientific community knows this. The wait for a different kind of instrument, one that can survey broad swaths of sky with consistent sensitivity, neither biased toward any particular region nor limited to deep pointed observations, has been building for years. That instrument exists. It is becoming operational. But before the search reaches that turning point, a discovery made in 2023 arrived and quietly complicated everything. Sometimes the most important evidence is not what you find, but what you find that is suspiciously, impossibly quiet. The entire intellectual case for Planet 9 rests on a specific kind of logic. Something out there is disturbing things. The orbital clustering of the extreme trans-Neptunian objects, the 6-degree tilt of the planetary plane, both are signatures of gravitational influence. Something is pulling, something is nudging. The anomalies exist because a massive unseen body is reaching across hundreds of astronomical units and bending the paths of smaller objects toward its own gravitational preferences. The way a strong current beneath the surface of a river bends the path of everything floating above it, even when the current itself is invisible from the bank. That is the forward logic of the Planet 9 hypothesis. Disturbance implies a source. Find the geometry of the disruption, and you can work backward to infer the disturber its mass, its distance, its orbital orientation. This is the same reasoning that allowed Leverrier to find Neptune from an armchair, and the same reasoning that has guided every subsequent search for unseen bodies in the outer solar system. It is clean, powerful, and historically successful. In 2023, astronomers discovered an object that quietly, methodically, and completely inverted that logic, and in doing so, forced a recalibration of everything the models had assumed about where Planet 9 could be hiding. The object was cataloged as 2023 KQ-14. It belongs to the trans-Neptunian population, the broad, loosely organized family of bodies orbiting beyond Neptune in the cold outer reaches of the solar system. And its initial discovery was not accompanied by particular fanfare. new trans-Neptunian objects turn up with increasing regularity as survey technology improves and sky coverage deepens, and most of them confirm rather than complicate the existing picture of outer solar system architecture. They fill in the census, they add data points. Rarely do they change the conversation. 2023 KQ14 changed the conversation. When orbital analysts ran the object's trajectory backward through time using high-precision gravitational simulations, a standard procedure applied to newly discovered outer solar system bodies, designed to reconstruct orbital history and assess long-term dynamical stability, they found something that did not belong in the picture the models had been painting. The orbit of 2023 KQ14 was pristine, perfectly stable, undisturbed across millions of years of simulated history, with no sign of gravitational perturbation, no hint of external influence reshaping its trajectory at any point across the entire time frame the simulations covered. It moved through its region of space the way a ball rolls across a perfectly level floor, no deviation, no wobble, no accumulated record of outside forces acting on it across geological time. And here is precisely why that result landed with such weight. 2023 KQ14 occupies a region of space that, according to the original Battigan-Brown models published in 2016, sits well within the gravitational reach of Planet 9. If Planet 9 existed at the position, distance, and orbital configuration those models specified, its gravity should have been reaching this object across millions of years, tugging at its perihelion, shifting its orbital plane incrementally, leaving the kind of accumulated gravitational fingerprint that any sufficiently massive body leaves on smaller objects it passes near over deep time. No fingerprint existed. The orbit was clean in a way that, given the predicted proximity of Planet 9 in the original models, it had no obvious right to be. Picture a long stretch of interstate highway where, every 1,000 miles, a massive 18-wheeler passes through the adjacent lane at speed. The pressure wave from that truck, the wall of displaced air pushing ahead of it, hits every vehicle in nearby lanes. You feel it as a brief sharp lurch, a pull toward the truck as it approaches, then a push away as it passes, your steering wheel resisting you for a moment before the air stabilizes. Over millions of passes, across millions of years, every vehicle on that highway would carry some accumulated record of those encounters' subtle alignment drift, where patterns in the tires from constant micro-corrections, a trajectory that over time reflects the persistent low-level influence of that recurring pressure. Now imagine one vehicle on that same stretch of highway showing none of that. Same road, same time frame, no alignment drift, no tire wear from correction, no evidence in its entire mechanical history of having ever encountered a pressure wave from a passing truck. Two explanations survive. Either there was no truck traveling that highway, or the truck has been driving in a completely different lane, far enough removed from this particular vehicle that its pressure wave never reached it, never touched it, left no mark across the entire span of recorded history. 2023 KQ14 is that vehicle, and the question the data forces is not whether the truck exists. It is where, exactly, the truck has actually been traveling. You might read all of that and arrive at the intuitive conclusion, this sounds like a disproof. An object sitting in the region where Planet 9's gravity should dominate, showing zero gravitational disturbance across millions of years of simulation. Doesn't that simply mean there is nothing there to disturb it? That is the natural first reading. The scientifically correct reading runs in the opposite direction. 2023 KQ14 does not eliminate Planet 9. It eliminates a specific version of Planet 9, the one defined by the particular perihelion distance, orbital inclination, and sky position that the 2016 Battigan-Brown paper proposed as its initial best estimate. What the pristine orbit of this object actually accomplishes is not a refutation, but a constraint. It says, with the precision of a ruled line, Drawn across a map, whatever is out there cannot be here, in this configuration, at this distance. The search area shrinks. The remaining possibilities are pushed outward into darker and more distant territory. That is not a door closing, that is a door moving. When orbital analysts fed the 2023 KQ-14 data into updated simulations, the output produced a revised constraint set, Planet 9. If it exists, must have its perihelion at a distance greater than 500 astronomical units from the Sun farther out than the original models centered on. Alternatively, it must be traveling on an orbital plane more steeply inclined relative to the ecliptic than Badigan and Brown's initial proposal specified. Possibly both conditions apply simultaneously. A body sitting closer, or oriented more shallowly, would have left detectable traces on the orbit of 2023K Q14 across the millions of years the simulations covered. Those traces are absent. The constraint is real. The process of ruling out locations by finding undisturbed objects in those locations is, from the outside, a genuinely strange-looking form of scientific progress. You make a discovery, and the discovery's most important message is an absence, no perturbation, no fingerprint, no sign that the thing you are looking for was ever nearby. You report this to colleagues as an advance. The field agrees that it is. Finding a hidden planet by systematically cataloging the places it cannot possibly be hiding is a strategy that sounds almost deliberately perverse, but it is precisely how science operates when direct detection remains out of reach. You triangulate by elimination. You close off wrong answers until the right answer runs out of room to hide. The humor embedded in this situation is not entirely lost on the researchers doing the actual work. For years, the Planet 9 team has been explaining to funding bodies, journalists, and skeptical colleagues that their hypothesis rests on solid quantitative evidence. The most recent piece of evidence strengthening that case is an object that is scientifically significant precisely because of the absence of the signal the hypothesis predicts. Progress, in this particular search, has rarely worn a stranger face. 2023 KQ-14 didn't close the door. It just moved that door into a darker, more distant corner. When a prediction fails in its specifics, science does not discard the underlying framework. It adjusts the parameters, tightens the constraints, and runs the model again with better inputs. This is not a defensive maneuver or an act of intellectual stubbornness. It is the correct methodology, validated repeatedly across 4 centuries of scientific history, and it has produced some of the most important theoretical advances ever made. Newton's laws of motion and gravitation predicted planetary orbits with extraordinary precision across the vast majority of conditions encountered in the solar system. But Mercury's orbit refused to fully cooperate its perihelion, precessed at a rate 43 arcseconds per century, faster than Newtonian mechanics could explain. That discrepancy persisted for decades. Well measured, impossible to dismiss, deeply inconvenient. It did not cause physicists to abandon Newton. It revealed that Newtonian gravity was an excellent approximation of a deeper truth, rather than the complete truth itself. Einstein's general relativity provided the deeper framework, not by overturning Newton, but by showing where his equations broke down and what replaced them at the boundary. The revision sharpened the science. The foundational insight that gravity governs orbital motion survived intact, expressed more completely than before. The Planet 9 hypothesis is moving through a structurally similar adjustment. 2023 KQ-14 demonstrated that the specific parameters of the original 2016 Badigan-Brown proposal cannot all be simultaneously correct. The perihelion distance, the orbital inclination, the predicted sky position, at least some of those values need revision. The scientific response has been precisely what the history of physics would predict not abandonment, but recalibration. The revised picture, incorporating the constraints from 2023 KQ-14 alongside the full body of ETNO orbital data available through mid-2024, places Planet 9's most likely perihelion somewhere in the range of 500 to 800 astronomical units from the Sun. That is meaningfully farther than the original models centered on, and it has direct consequences for every aspect of the search. The orbital inclination, the angle at which Planet 9's path is tilted relative to the flat ecliptic plane where the 8 known planets reside, is now estimated somewhere between 15 and 25 degrees in the revised models. That is steeper than the initial proposal. And it matters because inclination determines which bands of sky a planet can actually occupy at any given point in its orbit. A more steeply inclined orbit sweeps through different regions of the celestial sphere than a shallowly inclined one, and ruling out the shallower configurations concentrates the remaining search into specific sky corridors that, while still expansive, cover less total area than an unconstrained all-sky problem. The orbital eccentricity, the measure of how elongated the orbit is, remains high and consistent with the dramatic ellipse the initial models described. Planet 9 is still predicted to swing between a relatively close perihelion and an enormously distant aphelion on a timescale of 10,000 to 20,000 years per orbit. That fundamental character of the orbit has not changed. What has changed is the specific location of the closest point, pushed outward by the evidence of one undisturbed object sitting in the region. The old models would have filled with gravitational influence. Consider a practical analogy that keeps the scale intuitive. You're searching for a specific individual somewhere in a large American city. At the start of the investigation, you have no information constraining the search. The person could be anywhere within the entire metropolitan area, in any neighborhood, on any block, inside any building, at any hour of the day or night. The search space is the full city. That was the original Planet 9 problem. New information arrives. Witnesses place the person away from 2 of the 5 boroughs during the period in question. The search area contracts. You are no longer combing all 5 boroughs, only 3 remain. The problem feels more tractable. But 3 boroughs of a major American city still contain hundreds of square miles of territory, thousands of blocks, millions of rooms. The reduction in search space is real and meaningful. The remaining challenge is still enormous. That compression genuine progress that still leaves an overwhelming task is approximately where the Planet 9 search stands after absorbing the lessons of 2023 KQ-14. The remaining candidate region of sky, even under the tightened constraints, spans thousands of square degrees, equivalent to thousands of times the apparent area of the full moon as seen from Earth on a clear night. At the faint optical and infrared magnitudes where Planet 9 is predicted to fall, systematically covering that region to the sensitivity depth required for detection exceeds the combined capacity of every survey program currently operating. The neighborhood has been identified. The house has not been found, and the instruments needed to search the neighborhood properly are only now coming online. What the updated models do not produce is any ETNO with a well-characterized orbit that flatly contradicts the existence of Planet 9 itself. The distinction between contradicting a specific set of parameters and contradicting the hypothesis deserves to be held clearly and precisely. 2023 KQ-14 ruled out a configuration. It did not rule out a planet. Through mid-2024, the clustering signal in the ETNO orbital data contested in magnitude, variable across different analyses depending on sample selection and treatment of observational bias, but present has not disappeared. The 6-degree tilt of the planetary plane relative to the solar equator has not been explained by any mechanism operating within the known 8-planet system. Both anomalies that launched this search a decade ago remain in the data, unresolved, pointing toward the same general region of the outer solar system. The map has been redrawn. It is more precise than the original, more constrained by actual observations, more honest about where the remaining uncertainty actually lives. The search has not ended. It has been pushed outward and upward on the celestial sphere, toward darker sky and greater distance, into territory that will require better tools than currently exist to fully explore. And while the orbital dynamicists were busy revising their maps and adjusting their parameters, a separate group of researchers at one of the most prestigious institutions in the world had quietly stopped asking where Planet 9 was and started asking whether it was a planet at all. Sometimes the most outrageous question turns out to be the right one, and its answer is no smaller than a grapefruit-sized black hole. Black holes, in the public imagination, are the products of catastrophe at the largest possible scale. A star many times more massive than the Sun burns through its nuclear fuel over millions of years, then exhausts that fuel in a final, spectacular collapse. The outer layers explode outward in a supernova. The core, suddenly unsupported, crushed under its own gravity in a fraction of a second, compresses beyond any density the universe normally permits, folding space around itself so tightly that not even light can escape. The result is a black hole, a region of space-time where gravity has won so completely that the concept of surface no longer applies. And anything crossing the event horizon is gone from the observable universe forever. That is the version most people carry. Massive star, violent death, enormous remnant. The scale of the process matches the scale of the outcome. Something catastrophic produces something catastrophic. In 2019, a paper appeared in monthly notices of the Royal Astronomical Society letters that quietly proposed something the standard picture had never made room for. The authors were Jakob Schultz at Durham University and James Unwin at the University of Illinois at Chicago. And their proposal was the gravitational anomaly pulling at the edges of the solar system, the thing bending ETNO orbits, tilting the planetary plane, resisting every attempt at optical or infrared detection, might not be a planet at all. It might be a black hole, not a stellar mass black hole born from a dying star, something far older, far smaller, and far stranger. A primordial black hole. The distinction matters enormously. Primordial black holes did not form from collapsing stars. They formed from the universe itself, in the first fraction of a second after the Big Bang, when the cosmos was so dense and so violently compressed that regions of space could spontaneously collapse into black holes before any stars, any galaxies, or any atomic nuclei had time to exist. The mechanism required no stellar evolution, no supernova, no millions of years of nuclear burning. It required only pressure, the raw, almost incomprehensible pressure of a universe that had just begun and had not yet learned how to be anything other than an inferno of compressed energy. Think of it as a bullet forged in the first instant of creation, not cast from metal, not shaped by any hand, simply squeezed into existence by conditions so extreme that space itself buckled and locked a piece of itself away permanently. Before the universe had cooled enough to permit the formation of a hydrogen atom, the primordial black hole carries no memory of a star. It is older than stars. It is, in a very literal sense, a relic of a universe that no longer exists in any form we would recognize. Schultz and Unwin's proposal placed one of these ancient relics in our own solar system, captured into a long, elliptical orbit around the Sun, sitting somewhere around 700 astronomical units away, silently doing what black holes do, curving the space-time around it, tugging at everything nearby, completely invisible to every instrument we have ever built. Now for the number that reframes everything. The primordial black hole proposed by Schultz and Unwin would carry a mass equivalent to roughly 5 to 10 times the mass of Earth. That matches the gravitational signature of Planet 9, almost exactly the same mass range derived from the same orbital anomalies. In that sense, the mathematics of a primordial black hole and the mathematics of a planet are indistinguishable. Both fit the data. Both produce the observed clustering. Both explain the tilt. But the physical object itself would be nothing like a planet. A black hole of 5 to 10 Earth masses would have a Schwarzschild radius, the radius of its event horizon, the boundary from which nothing returns, of roughly 4 to 5 centimeters. The full diameter of the object, in the sense of the region from which no light escapes, would be somewhere around 8 to 9 centimeters, smaller than a grapefruit. An object with the gravitational muscle to reshape the outer solar system, bend the orbits of worlds hundreds of astronomical units away, and tilt the collective orbital plane of 8 planets sitting in an area you could hold in 2 cupped hands. No surface, no atmosphere, no reflected light, no thermal emission detectable by any instrument currently in operation or currently planned. The Hawking radiation, it produces the faint quantum leakage that is the only energy a black hole of this mass would emit, falls so far below the sensitivity threshold of any detector humanity has built that it contributes nothing to any practical search strategy. It is not merely dark, it is physically fundamentally undetectable by every electromagnetic method we possess. If the thing pulling our solar system into its current shape is an invisible black hole orbiting the sun, how would we ever know? That question does not have a comfortable answer, and the discomfort is not philosophical, it is operational. Every search strategy developed for Planet 9 assumes that the target emits or reflects something. Optical surveys look for reflected sunlight. Infrared scans look for thermal emission from a warm interior. Even the Akari candidates, ambiguous as they are, rested on the assumption that the object in question was radiating energy in some detectable form. A primordial black hole at 700 astronomical units produces no reflected light because it has no surface to reflect from. It produces no infrared glow because it has no warm interior. It produces Hawking radiation at a temperature so vanishingly small, far colder than the cosmic microwave background itself, that the signal is drowned out before it travels any meaningful distance. Every tool pointed at the sky comes back with the same answer, nothing there. Because from the perspective of any electromagnetic detector, nothing is there. The black hole exists in gravitational terms only. It bends space, it tugs at orbits. It has been doing exactly that in complete silence, potentially for billions of years. A grapefruit-sized object, 10 times the mass of Earth, orbiting the sun once every 15,000 years, leaving no light, no heat, no signal of any conventional kind, just the slow, patient distortion of everything moving nearby. If you wrote that into a science fiction novel and submitted it to a publisher, the editor would hand it back with a polite note explaining that readers will not accept physics this absurd, and yet the mathematics permits it. The orbital data does not rule it out, and the people proposing it work at 2 of the most respected research institutions in the world. The primordial black hole hypothesis doesn't just fit the mathematics. It pulls an even larger question into view about the origin of the universe itself, one that science has not yet answered. When 2 competing hypotheses both explain the same set of observations with equal mathematical precision, science has a traditional tool for choosing between them, Occam's razor. The principle, attributed to the 14th century philosopher William of Ockham, holds that among explanations of equal predictive power, the simpler one is generally preferable. Not because the universe is obligated to be simple, it demonstrably is not, but because simpler explanations carry fewer unverified assumptions, and every unverified assumption is a place where the reasoning can quietly break down. By that criterion, a planet wins over a primordial black hole without much contest. Planets are known to exist. The solar system formed from a disk of material that almost certainly had enough mass and the right conditions to produce additional planets beyond what we currently see. Ice giants like Uranus and Neptune are well understood objects with documented physical properties. A Planet 9, built from rock and ice and compressed volatiles, is strange only in its distance and orbital eccentricity in every other respect. It fits within the established inventory of things the universe makes routinely. A primordial black hole in orbit around the Sun is something else entirely. No primordial black hole has ever been directly confirmed to exist anywhere in the universe. Their existence is theoretically permitted by the physics of the early universe, and there are cosmological reasons to think some number of them formed in the first moments after the Big Bang. But the observational evidence for the population remains indirect and contested. A primordial black hole captured into a stable solar orbit represents not one, but two unconfirmed phenomena stacked on top of each other: the existence of primordial black holes as a population, and the capture mechanism that would have brought one into gravitational partnership with the Sun. Occam's razor points firmly at the planet. The universe, however, does not always consult Occam's razor before making decisions. What Schultz and Unwin identified, and what gives their proposal genuine scientific traction beyond its obvious shock value, is that the primordial black hole hypothesis accomplishes something a planet cannot. It solves two separate problems with one object. The first problem is the one this entire story has been building toward: the ETNO orbital clustering and the 6-degree tilt of the planetary plane, both of which require a gravitational perturber of roughly 5 to 10 Earth masses at several hundred astronomical units. A planet solves this problem. So does a primordial black hole of equivalent mass. On this specific point, the two hypotheses are mathematically identical. The second problem is cosmological, and it operates at a completely different scale. Astronomers and physicists have long grappled with the question of what dark matter actually is. The evidence for dark matter's existence is overwhelming galaxy rotation curves, gravitational lensing, large-scale structure formation, the cosmic microwave background. But the identity of the particles or objects that constitute dark matter remains one of the most significant unsolved problems in all of physics. Among the candidate explanations is a population of primordial black holes distributed throughout the universe, their combined mass contributing to the gravitational effects we attribute to dark matter. Observations of gravitational microlensing events, moments when a massive compact object passes in front of a background star and briefly brightens it, through gravitational focusing, have constrained but not eliminated the primordial black hole dark matter hypothesis. Schultz and Unwin calculated that if primordial black holes with masses in the range of 5 to 10 Earth masses constitute somewhere between 1 and 2% of the total dark matter in the Milky Way, the probability of the Sun having captured at least one such object into a bound orbit over the lifetime of the solar system falls within what they described as statistically reasonable bounds. One object, two problems addressed: the solar system anomaly and a piece of the dark matter puzzle, both potentially explained by the same ancient invisible relic of the universe's first instant. That is a genuinely powerful feature of the hypothesis, and it is why the paper attracted serious attention rather than being dismissed as speculation. When a single proposed object simultaneously accounts for local gravitational anomalies and connects to one of the largest open questions in cosmology, the scientific community pays attention even if the object itself defies every conventional detection strategy. And defy them, it does, completely. No wavelength of electromagnetic radiation can reveal a primordial black hole at 700 astronomical units. Optical telescopes find nothing: no surface, no reflected light, nothing to scatter photons back toward the detector. Infrared instruments find nothing, no thermal emission, no warm interior, no energy budget that produces detectable heat. X-ray and radio observations find nothing, the accretion of interstellar medium onto an object this small and this isolated in the near vacuum of the outer solar system generates no meaningful signal. The Hawking radiation temperature of a 5 Earth mass black hole is so extraordinarily low, billions of times colder than the cosmic microwave background, that detecting it from Earth is not a technology problem awaiting a better instrument. It is a physics problem with no foreseeable solution. The only detection pathway that survives theoretical scrutiny is gravitational microlensing, catching the moment when the black hole passes in front of a background star and amplifies that star's apparent brightness through gravitational focusing. This has been done for other microlensing events in the galaxy. It could, in principle, be done for a primordial black hole in the outer solar system. But microlensing surveys require knowing where to look and when, because the alignment between observer lensing object and background star must be nearly perfect, and the event lasts only days to weeks. Without a known orbital trajectory to predict where the black hole will be, organizing a targeted microlensing search is equivalent to waiting for a specific needle to pass through a specific point in a haystack the size of the continental United States. The detection problem for a primordial black hole is, in the bluntest terms, potentially permanent with current physics. We cannot see it. We cannot heat map it. We cannot catch its radiation. We can only infer its presence from the gravitational shape it leaves on surrounding space, the same inference that started this entire search. The same orbital anomalies that led Badigian and Brown to propose a planet in the first place. And this is precisely where another group of scientists stepped in, not to argue for a planet or a black hole, but to challenge the very foundation on which both hypotheses rest. Before you name the thing you cannot see, make sure you are not being deceived by your own eyes. Observational bias is not an exotic concept reserved for the philosophy of science. It operates in every field where humans collect data, and its consequences range from inconvenient to catastrophic, depending on how long it goes unrecognized. Consider what happened in cardiology for most of the 20th century. Heart attacks in women were systematically underdiagnosed, not because women experienced them less frequently, but because the medical literature had been built almost entirely on studies of male patients. The textbook symptoms, crushing chest pain radiating down the left arm, shortness of breath, cold sweat, those descriptions were accurate for men. Women experiencing cardiac events often presented differently with jaw pain, nausea, fatigue, or discomfort that didn't match the standard picture at all. Physicians trained on male-centered data looked at female patients through male-centered diagnostic criteria and saw something that didn't quite fit, and too often concluded it wasn't a heart attack. The data wasn't lying. The framework for interpreting the data was built on a biased sample. The bias produced systematically wrong conclusions for decades before the medical community recognized and began correcting it. The lesson generalizes when your instrument, whether it's a stethoscope, a statistical model, or a telescope, only looks in certain places. The pattern you find may reflect where you looked rather than what actually exists. In 2019, the same year, Schultz and Unwin published their primordial black hole proposal. Astronomer Samantha Lawler at the University of Regina and her collaborators published an analysis that aimed directly at the observational foundation of the Planet 9 hypothesis. Their target was not the 6-degree tilt of the planetary plane that anomaly sits in its own category. Derived from properties of the Sun and the 8 known planets, immune to the specific critique they were mounting, their target was the ETNO orbital, clustering the apparent alignment of distant icy objects that Trujillo and Shepard had identified between 2003 and 2016. and that Badigan and Brown had used as the primary quantitative basis for their Planet 9 proposal. Lawler's team asked a simple, devastating question. Where exactly were the telescopes looking when those clustered objects were discovered? The answer was not comfortable for the Planet 9 camp. The extreme trans-Neptunian objects, whose orbital perihelia appeared to cluster in the same direction of sky, had not been discovered through uniform, unbiased surveys of the entire celestial sphere. They had been found during targeted observations of specific sky regions that happened to be favored by the large survey programs and dedicated telescope time that existed at the time. The clustered objects came disproportionately from a limited portion of the sky, specifically the portions that ground-based survey programs had covered most thoroughly. The implication cuts to the heart of the hypothesis. If the telescopes had been looking predominantly in one direction, and all the clustered objects were found in that direction, then the clustering might not reflect a real physical alignment caused by a distant planet's gravity. It might simply reflect where the cameras were pointed. The pattern could be a statistical artifact, a phantom structure created not by an unseen world, but by the boundaries of human observation. Think of it this way. You are searching a parking lot at night for lost keys. The parking lot stretches in every direction, but there is only one functioning streetlight, positioned in the northwest corner. You look under that light, because that is where you can actually see. You find 6 keys, all clustered in the northwest corner. You might conclude that keys cluster in the northwest corner of parking lots. Or you might notice that you only searched one corner, and that the 6 keys tell you something about where you looked, not about where keys tend to be. Lawler's team ran simulations. They modeled what a biased survey would find if the true population of extreme trans-Neptunian objects was randomly distributed, no clustering, no external perturber. Just the chaotic distribution physics would predict in the absence of a Planet 9. The result was striking, given the observational biases present in the surveys that produced the original Planet 9 evidence. A randomly distributed population of ETNOs would still appear clustered in the limited sky regions that had been most thoroughly searched. The apparent clustering, in other words, was fully consistent with no planet existing at all, as long as you accounted for the fact that the telescopes hadn't looked everywhere equally. If we have only searched half the sky, how do we know the other half isn't full of unclustered objects that no one has seen yet? That question does not have a clean answer, and it matters because the entire quantitative case for Planet 9, the less than 0.007% probability of random clustering that appeared in the original Badigan-Brown paper, was calculated under the assumption that the discovered objects represented an unbiased sample of the ETNO population. If the sample was biased, that probability estimate is wrong. Perhaps dramatically wrong. Lawler and her collaborators concluded that with fewer than 20 objects used as the primary evidence, the actual number of well-characterized ETNOs available at the time of the 2016 proposal, the apparent orbital clustering was fully explainable as a statistical illusion produced by observational selection effects. No planet required, no black hole required, just telescopes that hadn't looked everywhere yet. Finding a pattern in the places they had bothered to look, Badigan and Brown did not accept that conclusion without response. Their counter-argument acknowledged the observational bias problem as a legitimate concern while disputing the magnitude of its effect, even after applying corrections for the known biases in the survey data. They maintained the probability of the observed clustering arising from a randomly distributed population remained below 1 to 2%. That residual signal small, but non-zero even after bias correction, kept the hypothesis scientifically alive. A 1 to 2% probability of chance occurrence is not proof of anything, but it is also not nothing. It is an anomaly that has survived scrutiny, diminished but not eliminated. The two sides of this debate are not talking past each other. They are genuinely disagreeing about how much the observational bias corrections change the statistical significance of the clustering signal, and that disagreement cannot be resolved by argument. It can only be resolved by better data. Specifically, it requires data from surveys that covered the entire sky uniformly, without favoring any particular region, without the historical accident of telescope time allocations pointing certain cameras at certain patches of sky more often than others. What the Planet 9 debate needs, at its most fundamental level, is a census of the outer solar system that is genuinely complete, or at least far more complete than anything achieved before 2025. Until that census exists, the observational bias critique cannot be fully answered, and the hypothesis cannot be fully confirmed or dismissed. Both sides know this. The argument has reached the boundary of what existing data can settle. Further debate without better data produces diminishing returns. This argument cannot be resolved by reasoning alone, only by data that is comprehensive enough, uniform enough, and unbiased enough to settle it. In statistical science, the threshold for calling a finding real rather than noise is expressed through a measure called the p-value, the probability that the observed result could have occurred by chance if nothing real were actually happening. The conventional threshold in most fields of science is a p-value below 0.05, meaning a less than 5% chance the finding is random. Cross that line, and the result is considered statistically significant, worth publishing, worth taking seriously. Particle physics holds itself to a much higher standard. When researchers at the Large Hadron Collider announced the discovery of the Higgs boson in 2012, the evidence had reached what physicists call 5 sigma, a statistical threshold corresponding to a probability of roughly 0.0003% that the signal was a random fluctuation, 1 in approximately 3.5 million. That is the bar particle physics requires before the word discovery is permitted to appear in a press release. The reason for that elevated standard is hard experience. The history of particle physics is littered with 3 sigma and 4 sigma signals that generated enormous excitement, consumed significant resources, and eventually dissolved as more data came in. The field learned painfully that preliminary statistical significance is not the same thing as reality, and it adjusted its standards accordingly. The Planet 9 evidence currently sits somewhere between 1 sigma and 3 sigma, depending on which objects are included in the analysis, how observational bias corrections are applied, and which statistical framework is used to evaluate the clustering signal. That range is not a fixed number. It shifts as new E, T, N, O's are discovered, as bias corrections are refined, and as different research groups approach the data set with different methodologies. But the general territory is consistent above the threshold of probably worth investigating, well below the threshold of we are confident this is real. 1 sigma, in practical terms, means the finding is interesting enough to look into further. 3 sigma means it is interesting enough to build a dedicated research program around. 5 sigma means you call the press. Planet 9, at its current evidential standing, lives in the uncomfortable middle zone, the region of science where something is too significant to ignore and too uncertain to announce. Historically, this is exactly where discoveries go to die, consumed by later data that reveals the original signal was noise. It is also where some of the most important discoveries in history have gestated before enough evidence accumulated to confirm them. The honest answer about where Planet 9 currently stands is no one knows yet. The signal is real enough that serious researchers at serious institutions have devoted years to the search. It is uncertain enough that other serious researchers at equally serious institutions argue the signal may not require a planet to explain it. Both positions are defensible with the available data. Both will remain defensible until better data arrives. Think of sigma levels as the scientific system for measuring how real something actually is. If 1 sigma is the moment you notice something odd and say, "Huh, that's interesting," 3 sigma is when you call your colleague at midnight and say, "You need to see this." 5 sigma is when you call the Nobel Committee. Planet 9 is stuck at the "let's get more data before we get excited" level, which is frankly the most uncomfortable place in all of science to spend a decade. The observational bias critique raised by Lawler's team applies with full force to the ETNO clustering signal. It does not apply to the 6-degree tilt anomaly. And this distinction is crucial because it means the 2 pieces of evidence underpinning the Planet 9 hypothesis have different levels of vulnerability to the bias argument, and understanding which is which determines how much of the hypothesis survives even the strongest version of the skeptical critique. The ETNO clustering was discovered through biased surveys. The clustering signal may be partially or wholly an artifact of where those surveys pointed. That vulnerability is real, acknowledged by the Planet 9 proponents themselves and unresolved. The 6-degree tilt of the planetary plane is a different kind of evidence entirely. It was derived not from surveys of distant icy objects, but from measurements of the Sun's rotational axis, the helioseismological data that established where the solar equator actually points compared against the well-characterized orbital mechanics of the 8 known planets. No survey bias affects this measurement. It doesn't matter which patch of sky any telescope was pointed at. The tilt is a property of the solar system's internal geometry, measured directly from objects we have known about for centuries. It exists whether or not any ETNO has ever been observed. This is the strongest remaining pillar of the Planet 9 hypothesis, an anomaly that cannot be explained away by observational selection effects. That sits in the data independently of the clustering debate. And that still lacks any convincing explanation other than a distant external perturber. As long as the 6-degree tilt exists unexplained, and it does, the complete dismissal of the Planet 9 hypothesis requires accounting for something the observational bias argument does not touch. The current state of the debate, rendered honestly, is this: one side says the evidence is sufficient to justify continued searching. The other side says the evidence is insufficient to justify confident belief. Both sides are correct simultaneously, without contradiction. One group is making a claim about the value of the search as a scientific investment. The other is making a claim about the epistemic status of the hypothesis given current data. Those are different claims about different things, and they are not in conflict with each other as much as they appear to be from the outside. Both camps are waiting for the same thing: a data set comprehensive enough, uniform enough in its sky coverage, and sensitive enough in its detection limits to either reveal the clustering as real across the full celestial sphere or dissolve it into the uniform distribution that a bias-dominated false signal would produce once the gaps in coverage are filled. That dataset does not yet exist in complete form, but the instrument designed to produce it has begun operations. The final answer is not hiding in any argument. It sits on a hillside in Chile, where a telescope is just beginning to turn its eye to the sky. The great questions in astronomy have rarely been settled by argument. They have been settled by instruments. For most of the 20th century, cosmologists debated whether the universe's expansion was slowing down under its own gravity, holding steady, or accelerating. The mathematics permitted all 3 possibilities depending on assumptions about density and initial conditions. Theorists argued across decades, constructing elegant frameworks that supported whichever answer their starting assumptions favored. The debate was genuine, serious, and unresolvable by reasoning alone, because reasoning, in the absence of sufficient data, can be bent to support almost any conclusion a sufficiently skilled physicist wants to reach. The question was settled not in a seminar room, but in two independent observational programs in the late 1990s, both studying the brightness of distant Type 1a supernovae. When the data came back, it was unambiguous. The expansion is accelerating, driven by something the field was forced to call dark energy because it had no better name for it. The Hubble Space Telescope provided the observational leverage that made that measurement possible. Theory followed the instrument. LIGO, the Laser Interferometer, Gravitational Wave Observatory, detected gravitational waves in 2015 from the merger of two black holes more than 1 billion light-years away. For a century after Einstein's general relativity predicted that mass in motion would ripple space-time, physicists debated whether the waves would ever be measurable, whether the technology could ever reach the required sensitivity, whether the signal existed in a form detectable above noise. LIGO resolved all of it in a single 4-second event. The instrument produced the answer that argument could not. The James Webb Space Telescope has been observing galaxies from fewer than 500 million years after the Big Bang, objects so old and so distant that their light has been traveling toward us for more than 13 billion years. Questions about the earliest epochs of cosmic structure formation, debated theoretically for decades, are now being answered image by image as Webb's data accumulates. Every time astronomy has faced a question at the boundary of what existing instruments could address, the resolution has waited for a new tool capable of reaching past that boundary. The Planet 9 question is no different. The instrument that may finally settle it has a name, a location, and a camera the size of a small car. The Vera Rubin Observatory sits on Cerro Pachón in the Andes of north-central Chile, at an elevation of approximately 8,800 feet above sea level. The site was chosen for its exceptional atmospheric clarity, its dark skies, and its position in the southern hemisphere, which provides access to portions of the Milky Way and the southern celestial sphere that northern hemisphere observatories cannot reach effectively. The observatory is named for Vera Rubin, the American astronomer whose meticulous measurements of galaxy rotation curves in the 1970s provided some of the most compelling early evidence for the existence of dark matter. It is a fitting tribute, an instrument designed to probe the unknown, named for a scientist who spent her career making the invisible visible. The telescope is built around the largest digital camera ever constructed for astronomical purposes, 3,200 megapixels, capturing an image of the sky covering approximately 9.5 square degrees, roughly 45 times the apparent area of the full moon in a single 15-second exposure. At that image scale and that cadence, the Rubin Observatory can photograph the entire visible sky accessible from Chile in approximately 3 nights of normal observing conditions. Then it photographs it again and again for 10 years. The scientific program driving this cadence is called the Legacy Survey of Space and Time, LSST. Beginning its full science survey operations in 2025, LSST will accumulate 10 years of continuous uniform, all-sky imaging at depths and cadences no previous ground-based survey has approached. Every patch of accessible sky will be visited hundreds of times over the survey's lifetime. Every faint, slow-moving object in the outer solar system that reflects enough light to exceed the camera's detection threshold will, over time, leave a trail of detections in the archive, its position shifting from image to image at the slow angular rate characteristic of distant trans-Neptunian objects, distinguishable from background stars and galaxies by precisely that motion. What makes Rubin transformative for the Planet 9 question is not simply its sensitivity, though that sensitivity is extraordinary. What makes it transformative is its uniformity. Every critique of the existing ETNO clustering evidence reduces, at its core, To the same problem, the surveys that produced those objects were not uniform. They pointed at some parts of the sky more than others. They had gaps, biases, and coverage inhomogeneities that contaminated the statistical analysis of whatever they found. Lawler's 2019 critique was devastating precisely because it exposed how thoroughly the clustering signal was entangled with the observational selection effects of the surveys that produced it. Rubin severs that entanglement. By photographing the entire accessible sky on a 3-night cadence, with the same telescope, the same camera, and the same detection thresholds applied uniformly across every square degree of sky it covers, the observatory produces a data set in which observational bias of the kind that plagued the original Planet 9 evidence is structurally impossible at the same level. There is no patch of sky that gets more attention than any other. There is no region favored by historical telescope scheduling or the locations of particular research institutions. The census is as close to complete and uniform as ground-based astronomy from a single site can achieve. This is what Vera Rubin is, in its deepest function, not merely a telescope, but a cosmological lie detector. Point it at the sky for 10 years with no thumb on the scale, no preferred direction, no bias toward any particular answer, and whatever pattern emerges from the data is as close to the truth as current technology can get. If clustering exists in the ETNO population across the full sky, Rubin will see it. If it does not exist, if the apparent clustering was always an artifact of incomplete coverage, Rubin will dissolve it into the uniform distribution it actually was. For the first time in the history of this search, humanity has built a machine capable of returning a definitive answer. Not possibly, not the data is suggestive, a genuine yes or no, backed by 10 years of uniform sky coverage and 60 petabytes of archived imaging data. The total data volume accumulated by LSST over the 10-year survey is estimated at approximately 60 petabytes. To put that number in terms that carry actual weight, 60 petabytes is roughly equivalent to the total information content of about 30 million average personal computers. Processing that volume of data, detecting moving objects, characterizing their orbits, cross-referencing them against prior detections, flagging candidates for follow-up requires automated pipelines and machine learning systems running continuously throughout the survey. The Rubin data system has been designed and tested for exactly this purpose, developed in parallel with the telescope hardware over more than a decade of engineering work. The scientific community has been preparing for Rubin's data for years. The Planet 9 search teams at Caltech and elsewhere have developed analysis pipelines specifically designed to ingest Rubin's ETNEO detections as they accumulate cross-matching new objects against the theoretical predictions, building up the statistical picture of outer solar system orbital structure with each new observing season. The machinery for turning Rubin's images into an answer about Planet 9 is ready. The question has been waiting for the data. This is the first time in human history that we have built a machine powerful enough to return a definitive answer, not maybe, not it seems like, but yes or no. But the verdict machine is not only looking for one thing, it will reveal which category the correct answer belongs to. And each category carries a different consequence for everything humanity thought it understood. A good experiment does more than confirm a hypothesis. It must also be capable of disproving it. This requirement that a scientific claim be falsifiable, that it make predictions specific enough to be wrong, is the criterion the philosopher Karl Popper identified as the dividing line between genuine science and something that merely resembles it. A hypothesis that can absorb any possible observation without modification, that bends to fit whatever the data shows, is not a scientific hypothesis at all. It is an unfalsifiable belief dressed in quantitative language. Real science makes predictions that could fail. The value of an experiment lies precisely in its capacity to return a negative result. Vera Rubin satisfies Popper's criterion completely. Its data will not merely add evidence to one side of the Planet 9 debate. It will, over the course of its 10-year survey, produce a data set comprehensive enough to force a definitive resolution one way or another. The three possible outcomes are not equally probable, and they do not carry equal implications. Each one leads to a different understanding of what the solar system actually is, and each one rewrites a different portion of what science thought it knew. The first scenario, the planet is real. If the legacy survey of space and time reveals that the orbital clustering of extreme trans-Neptunian objects persists across the full, uniformly covered sky, that the alignment survives the elimination of observational bias and appears in the complete data set with statistical significance that approaches or exceeds 3 sigma, the case for a physical perturber becomes very nearly airtight. And if, within that same data set, Rubin's imaging detects a slow-moving point source in the predicted sky region, shifting position from image to image at the angular rate consistent with an object at 500 to 800 astronomical units, the hypothesis transitions from compelling to confirmed. That confirmation would represent the largest discovery in planetary astronomy since the telescopic confirmation of Neptune in 1846 itself, the last time mathematics alone located a planet before a human eye saw it. A Planet 9 detection would mean the solar system has 9 planets. It would mean the current mental model of solar system architecture, taught in every school and printed in every textbook, is incomplete in a way that has been staring at us through the mathematics for decades. It would trigger an immediate cascade of new questions. How did it form out there? Or was it captured from another star system? Or was it ejected from the inner solar system in the violent early period of planetary migration? Each answer leads to a different history of the solar system we live in. The second scenario is quieter and in some ways more unsettling. If Rubin's full sky data shows the orbital clustering persisting with genuine statistical significance, the pattern real, not an artifact of bias, but the 10 years of imaging find no physical object in the predicted region of sky down to the survey's detection limits. The inference space narrows dramatically towards something that cannot be seen. A gravitational perturber that produces a real orbital signal but leaves no photometric trace is not a planet. Planets reflect light. Planets emit heat. Something that bends orbits without being visible to any instrument Rubin can deploy is, by elimination, something that emits and reflects nothing detectable, which points, uncomfortably but logically, toward the primordial black hole scenario that Schultz and Unwin proposed. That outcome would constitute the first indirect evidence that dark matter exists in the form of discrete compact objects within our own solar system. It would not be proof the absence of a detection in Rubin's data cannot rule out a planet that simply fell below the survey's sensitivity threshold in some configurations, but it would shift the probability distribution in a way that the scientific community could not ignore. The implications would extend far beyond the solar system into the fundamental question of what dark matter is and how it distributes itself throughout the galaxy. The third scenario is the one that would require the deepest reckoning. If Rubin's uniform, unbiased, all-sky survey of trans-Neptunian object orbits reveals that the clustering disappears, that the alignment seen in the original evidence dissolves into the uniform random distribution that physics predicts for an unperturbed outer solar system, then the conclusion is inescapable. The clustering was never real. It was always a product of where the telescopes happened to look, amplified by the natural human tendency to find patterns in incomplete data. The statistical anomaly that launched a decade of theoretical modeling, infrared searches, orbital simulations, and Harvard papers about primordial black holes was, from the beginning, an illusion and a very convincing one. That outcome would leave the 6-degree tilt of the planetary plane still unexplained, still sitting in the data without a mechanism, demanding a new theory that does not involve a distant perturber. It would also require a serious accounting within the scientific community for how a hypothesis built on such a thin initial evidential foundation attracted so much sustained attention and resources. Not a scandal science produces false leads regularly, and following them responsibly is part of the process, but a lesson about the difficulty of distinguishing signal from noise when the sample size is small and the sky is large. If scenario 3 happens, how many years have we spent fundamentally misunderstanding our own solar system? Science is the only human enterprise where you can spend 10 years, invest millions of dollars, and deploy the combined intellectual effort of hundreds of researchers across a dozen countries and arrive at the conclusion that nothing is there. No planet, no black hole, no perturber of any kind. Just an empty corner of the solar system that looked suspicious because the cameras had blind spots. And that result, delivered with sufficient rigor and completeness, counts as a complete success. The question got answered. The answer happened to be no. The field moves on, better informed. That is not failure. That is science doing exactly what science is supposed to do. But whatever the result turns out to be, the answer itself is less important than what this entire journey of searching has revealed about the nature of human understanding. Every generation of humanity has inherited a boundary question, something sitting at the outer edge of what that era's knowledge could reach. A problem too large for its time, left unresolved for the next generation to inherit, along with whatever tools and frameworks might finally be adequate to address it. Aristotle mapped the cosmos as a series of nested crystalline spheres, Earth at the center, the stars fixed to the outermost shell. The structure was elegant, internally consistent, and wrong in ways that could not be demonstrated with the instruments available to him. The boundary question he left behind: what is the actual architecture of the universe? And does Earth truly occupy its center? Waited nearly 2,000 years for Copernicus, Galileo, and Kepler to dismantle and rebuild. Newton gave physics the laws of motion and universal gravitation, transforming celestial mechanics from geometry into dynamics, and left behind the nature of light itself as his unresolved boundary. What was it, a wave or a particle? How did it propagate through empty space? That question consumed generations of physicists until Maxwell, then Einstein, then quantum mechanics. Each peeled back a layer, revealing that the answer was stranger than any of the original frameworks had permitted. Einstein himself closed some of Newton's open questions while tearing open new ones, the reconciliation between general relativity and quantum mechanics. Unresolved to this day is the boundary question he handed forward to the 21st century. The pattern across all of these is consistent. The generation that asks the question cannot answer it. The tools don't exist yet. The conceptual frameworks aren't adequate. The question sits at the edge of the possible and waits. The Planet 9 question fits that pattern in most respects, but it differs from all its predecessors in one way that has no precedent in the history of science. And that difference is worth sitting with for a moment before moving forward. Every prior boundary question involved something humanity could not yet see because the instruments were not sensitive enough, not powerful enough, not precisely enough calibrated to detect the signal. Galileo's telescope was not adequate to resolve stellar parallax. 19th century spectroscopes were not adequate to identify the quantum nature of atomic emission lines. Mid-20th century detectors were not adequate to register gravitational waves. In each case, the obstacle was technological. Build a better instrument, and the answer would follow. The Planet 9 boundary question is potentially different in kind. If the object responsible for the gravitational anomalies is a primordial black hole If Schultz and Unwin's 2019 proposal reflects reality rather than creative speculation, then the boundary we face is not technological at all. It is physical. No instrument built from any material, operating at any wavelength, positioned at any location in the solar system, can directly detect a 5 to 10 Earth mass primordial black hole at several hundred astronomical units. The invisibility is not a function of our current engineering limitations, it is a function of the physics of the object itself. We would be facing, for the first time in history, a boundary question whose answer may be permanently inaccessible to direct observation, knowable only through inference, through the gravitational shape the object leaves on everything around it, never through any direct signal the object itself produces. That is a qualitatively different kind of not knowing. Not we cannot see it yet. Possibly we can never see it directly, in principle, regardless of how far technology advances. The boundary, in that scenario, is not a wall waiting to be climbed. It may be a wall with no ladder. The decade that begins now is when this distinction gets tested. Vera Rubin Observatory commenced its full science survey operations in early 2025. The legacy survey of space and time, running continuously for 10 years, is accumulating data at a rate and uniformity that no previous survey has achieved. The Bannigan-Brown Research Group at the California Institute of Technology, the team that published the original Planet 9 hypothesis in 2016 and has refined it through every subsequent observational constraint, has spent years developing analysis pipelines specifically designed to process Rubin's ETNO detections as they arrive. The infrastructure for turning Rubin's images into statistical answers about outer solar system orbital structure is not being built reactively. It was built in anticipation, ready to receive the data the moment the survey began producing it. The timeline the scientific community currently projects is not vague. Based on the expected accumulation rate of ETNO detections, the rate at which orbital characterization improves as objects are observed across multiple oppositions, and the statistical power that accrues as the sample size grows. The first publications carrying genuine high significance statistical conclusions about the ETNO clustering question are anticipated in the period between 2027 and 2029. That is not the end of the survey. The full 10 years of LSST data will not be complete until approximately 2035. But orbital clustering analysis does not require waiting for the final data set. It requires enough objects with well-characterized orbits, distributed across enough of the sky, to distinguish a real pattern from a bias artifact with confidence. That threshold is expected to be crossed within the survey's first 3 to 4 years of full operation. By 2029, possibly earlier, there will be a real answer. Not a definitive final word on the physical nature of the perturber, if one exists, but a real, statistically robust answer to the foundational question, is the clustering genuine? Or was it always an artifact of incomplete observation? If the clustering is genuine, the decade of judgment will have delivered the most important target list in the history of outer solar system astronomy. A sky region constrained by real statistical evidence, pointing at something real. The search enters a new phase 1, where the question is no longer whether to look, but exactly where and how to look with instruments capable of the deepest possible sensitivity. If the clustering dissolves into randomness, the decade of judgment will have delivered something equally important: the closure of a decade-long wrong turn, achieved with enough rigor and completeness to be authoritative. The 6-degree tilt will remain still unexplained, demanding a new framework that the Planet 9 hypothesis cannot provide. The field will move forward with a cleaner slate and a harder problem. Either answer is a genuine truth about the solar system. Either answer advances understanding, the The process of getting there, building the instruments, designing the surveys, running the simulations, arguing about the statistics, finding 2023K, Q14, and revising the models, proposing primordial black holes and working out why they're almost impossible to detect. That entire process has already produced knowledge that would not otherwise exist. Science does not only advance when the hypothesis is confirmed, it advances every time a question is asked rigorously enough that the answer, whatever it turns out to be, is worth knowing. The Rubin Observatory is turning. The data is arriving. The pipelines are running. Somewhere in the 60 petabytes that will accumulate over the next decade. The answer to one of the most consequential questions in modern planetary science is already being written, one image at a time, by photons that left distant icy objects millions of miles away and fell, finally, onto the largest digital camera ever built for the purpose of reading the sky. Sometimes the greatest question is not what is it, but who are we, standing before it, not yet knowing. 6 compass needles pointing the same direction, a solar system tilted 6 degrees in a way that 4.5 billion years of physics cannot internally explain. A planet that mathematics demands, but no telescope has confirmed. A grapefruit-sized object that might outweigh 10 Earths and emit nothing detectable by any instrument humanity has ever constructed. This is not a technical question dressed in the language of science. It is a philosophical one, wearing the costume of orbital mechanics, asking, at its deepest level, whether the system we call home is the complete system, or whether we have been living inside something larger, stranger, and more indifferent to our certainty than we have been comfortable admitting. Science does not yet have the answer, and that absence, that open, unresolved, honestly acknowledged gap in human knowledge is not a weakness. It is the most accurate thing science has ever said about itself. We are a species capable of recognizing the boundary of what we know and refusing to pretend it isn't there. Vera Rubin is turning. The data is accumulating. In the years ahead, humanity will receive either a confirmed world or a confirmed void, and both will be true, and both will matter, and neither will be the end of the question. The edge of understanding is not a wall, it is a horizon, and the only way to reach it is to keep moving toward it, knowing it will always recede, and going anyway. We are still asking, which means we are not finished yet.